Okay, classwork 7.4 gets us to applications, sinusoidal applications. Sinusoidal applications are basically when you're dealing with waves. Now, we're familiar already with the word period, and that is a math word. Frequency is more of a physics word. So I'm going to come over here to the nice typed up answers. When you want to find the period of your trig function, you're going to take whatever your variable is directly multiplied by, and you are going to take a normal period length of 2 pi and divide it by b. That whatever that number is that is multiplying to your input variable. And the period is the length of time it takes to complete one cycle. However, in physics, they more frequently use frequency. Ha ha ha. Ha ha. More frequently they use frequency. Yeah. I guess I'm no Coda, huh? Coda's got puns all the time, I'm told. Okay, so frequency. Frequency is just the reciprocal of that because it's looking at the number of cycles per unit of time. So it's looking at, like, say, for example, per second, how many cycles does this wave go through? Or maybe it's per minute. How many cycles do we go through per minute? So it's just taking the reciprocal of the period. But it's helpful to be aware that frequency is the same thing as angular velocity, because it is looking at, angular velocity is looking at for one circular rotation, or what am I trying to say? That's right. One circular rotation is one cycle. So when you talk about angular, I'm tripping over my words. Angular velocity is looking at how much do I turn per unit of time. And one full rotation would be one cycle. That would be the same thing. So if it takes me 1 second to make 5 rotations, that's telling me about a frequency. All right, now, go back over here to example 1. Let's first understand what this problem is saying. We have a weight bobbing up and down on the end of a spring, and we're assuming this is an undamped system, which basically means that we're not going to lose any of that pull by gravity. We're just going, this thing is literally continuing to go back and forth without changing and slowing down. Because you know that give it enough time, it's going to slow down. So we're considering this in a system where this will not ever slow down. It'll just keep going back and forth the same amount. Now, the range of the vertical distance is 10 centimeters. And then you can see in the drawing that what that's referring to is there's a midline, and it goes up from that midline by 5 centimeters, and it goes down from that midline another 5 centimeters. So its range is 10 centimeters. But what you want to understand is that what you're given there is a high point, a low point, and a midline. Just like with the graphs that we draw of sine and cosine, with having a midline and then a high point and a low point. Those are an exact match, in fact. Now, you are told to assume the equilibrium, which is an at-rest position, is to be 0. So that means this midline is considered position 0. And then we're going to use the fact that up means positive. So this is going to be in the position of positive 5. This bottom is going to be in the position of negative 5. The time it takes for the weight to move from its maximum displacement above 0 to its minimum displacement below 0 and back again is 4 seconds. So that's saying that it's up here, and the amount of time it takes for it to go down and back again is 4 seconds. So from its highest point to its lowest, back up to its highest, is 1 cycle. And this wants to know the period of the system. The period of the system is how much time it takes to go through 1 cycle. So literally that number right there is telling you the period of the system. So what is the frequency of the system then? If I take the reciprocal of 4, I get 1/4. But that's representing what exactly? It's representing how many cycles you have per unit of time. So what it's saying is every 1 second that passes, you will only go 1/4 of the way through your cycle. So to go from the top to the midline, that's 1/4 of 1 cycle. And if it takes 4 seconds for it to travel from this point all the way back to this point, then the frequency is only 1/4 of a cycle per second. So hopefully that makes sense. Does that feel comfortable? It's so much easier when I can see people's faces, but having only 4 people to choose from is minimal. I hope everyone online is doing okay. And I'm going to walk you through these problems. Now, the next question is, what is the amplitude? And amplitude means the same thing it has meant before. What would you say is the amplitude? It's the distance from the midline to the highest point, which must also be the same as the distance from the midline to the lowest point. So it is 5 centimeters. On to part D. Assume that time begins when the weight is halfway through moving up. So if I'm halfway through moving up, and that's where I decide to start, let's first of all look at the picture and what that's saying. That's saying that my weight is right here at time 0, and it's on the way up, and then it hits its highest point. So let me ask you this. How long does it take to hit that highest point? If it's located here at time 0, what time is it located as it's at its highest point right after that? And you want to see that what that is that is actually 1/4 of its cycle. Because its cycle is head up, and then head down, and then head down, and then head up. And after doing those 4 movements, I have completed 1 cycle, and I'm back to where I started again, where it's at the center and on its way up. So what I'm looking at is, how long does it take me to go through 1/4 of a cycle? So that means that if this is my location at time 0 and I'm on my way up, then this is my location at time 1, because it will go through only a 1/4 cycle in 1 second. That also means that when I'm on my way down, I'm back at this position again at time 2. And then as I continue down, I'm at this position at time 3 seconds. And then another second later, and I'm back at 0 again for time 4. Now I've got to say, this diagram is a bit tricky to work with, because I'm trying to keep writing these arrows further over to kind of show what's going on, because if I just sit here and write it back and forth, you're not going to see. So what we do is we're going to draw a graph that is a sinusoidal graph. And this will match it perfectly if I am using a sine or a cosine function. But I can choose which function I want to use. Now, coming back to what part D says. It says, again, assume that time begins at t = 0 when the weight is halfway through moving up at its equilibrium position of y = 0. Write an equation of this form for the weight's height above or below its at-rest position of 0. So what that's trying to say is, if this is the y-axis and this is a time axis, then I am starting at y position 0 at time 0. At time 1 second later, I am at my highest point, which is 5. 1 more second later, I'm back to my y position 0. 1 second after that, I'm at my lowest y position, -5. And then 1 second later, I'm back to my center. And if you want, that's actually starting this graph. For parts D and E, you could actually figure either out in whatever order makes more sense to you. So I could actually just start graphing first and let that help me come up with the equation. So as I was saying, and I'm going to talk through it again, I am at y position 0 at time 0. I am at y position 5 at time 1 second later. I'm back to the center at time 2. I'm down to -5 at time 3. And I am back to the center of 0 at time 4. And I've actually got one cycle of that graph from putting that information together. For me personally, I like to draw the graph out. I like to see the picture of what's going on and then use that to help me understand the numbers in the equation. But everyone's different. Some people might see the equation first and then use the equation to graph. So I want you to know it's up to you because you can work it in different directions depending on the way you see the problem. Now realize that what we have here is an amplitude, positive or negative, and then that B is within the formula for frequency or the formula for the period of the graph, depending on which one you prefer to use, because you can actually use either one. Now, if I look at this graph, what is the amplitude? We can see that this is the midline. Can everyone see that the amplitude is 5 units? Also, if I have a sine function, the positive sine function starts at the middle and goes up before it goes down. And this does that. So that actually means that this is a positive 5. Now, I want all of you to think, how would you go about finding B with this information? And that's up to you how you want to go about it. It's valuable for you to think first, how would I do it, before you see someone else do it. There's a good chance you'll see a way different than the way I'm going to present to you. How long does it take to go through a cycle? Four seconds, right? That means that's the period of the graph. And I talked about the formula. Let me go back here. The period of a graph is always the length of a normal period length, 2 pi, divided by whatever number is multiplied here. That is equal to the period of the graph. We have a period that is equal to 4 seconds. So that means we're going to use the equation 2 pi over b equals 4. Now, if I want to solve for b, I can multiply the b over to the right side, and then divide by 4. And simplify. That simplifies to pi over 2. That is the b that goes right here. So finally, we have y equals 5 multiplied by the sine of pi times time over 2. And you can write it this way, or you can write it as pi over 2 times t, whichever way. And we have one cycle of the graph already drawn. Can you draw the next few cycles? I find it easiest to plot the ends of the quarter cycles and then draw from there. So this sinusoidal graph allows us to know the location, the vertical location of that weight based on how much time has passed. And it just keeps going through the same cycle over and over again. So that was our first example. Did you find that interesting? Maybe, maybe not. We've got more to come. So, example 2. If you've heard about the Ferris wheel, this is pretty similar to that as far as what we're doing with this. So let's take a look. Read the problem. Suppose that the water wheel in the figure rotates at 6 revolutions per minute. What does that mean as the frequency? If I make 6 revolutions per minute, what does that make my frequency? It's 6 per minute. But we want to look at it based on seconds. So if I need to cancel having minutes in the denominator, I want to cancel it with a having minutes in the numerator. And what is the ratio of minutes to seconds?
1/60.
Yep. And so I'm looking at what is 6 times 1/60. And that gives me an answer of 1/10 revolutions per second. And that is my frequency based on seconds. Next question. How many seconds have passed when point T reaches its maximum height for the first time? So now I'm going to start with reading the second sentence. This says 2 seconds after you start a stopwatch, point P on the rim of the wheel, there's point P, is at its greatest height of 13 feet. But that's 13 feet above the surface of the water. And here is the surface of the water. So how many seconds have passed when P reaches its maximum height for the first time? And that's 2 seconds. With the questions that I have for these problems, I'm trying to get you to realize what you want to look at when you're reading these word problems in the future. So it takes 2 seconds to reach its maximum height, and its maximum height is 13 feet if the surface of the water is considered height 0. So here's height 0. And now if you look at the drawing of this problem, this is saying that the radius is 7 feet. The distance from the center of that wheel to the surface of the water is only 6 feet. So what it's actually telling me, if I think about it, is that it has 1 foot of the wheel under the surface of the water. And then if I take the radius that is 7 feet and I draw that radius vertically, can you see that the distance above the water is 7 plus 6? So that means my high point is considered position 13. What is my low point? -1. And I find that because I know that from the center of the wheel, it goes down 6 feet down from that center and hits the water. There's 1 more foot of the radius to go. So -1 is the lowest point. Now the next question is, how many seconds have passed when P reaches its minimum height? And what is that minimum height? Now realize that 2 seconds pass to get me to this highest point. So I want to take that 2 seconds and I want to add how much time it takes for me to go from just the high point down to the low point. Do you see that that's actually half of a cycle? A full cycle would be going from the top all the way down to the bottom and all the way back up to the top to repeat again. So taking a good look at the information we have, how much time does it take to go from the top to the bottom? How much time does it take to go through half of a cycle? I'm getting some shrugs. You know, let me give you a minute to think about it. I'm just going to be quiet for a moment, and I want you to think about it. I'm going to pause the recording. Someone remind me to restart it back up. Okay. So, again, this is half of a cycle, which is half of a revolution. Every second, I go 1/10 of a revolution. So how much time does it take me to reach half of a revolution? So I'm looking at how much time I have one revolution per second, and I need to multiply that by a number of seconds to equal 1/2 of a revolution. And can some of you see that to make 1/10 go to 1/2, I need to multiply by 5. That's one way to look at it, but it's not the only way to look at it. So that means that it takes 7 seconds from where we start time to reach the minimum height, and the minimum height is -1. And I'm trying to remember, that was in feet. So -1 feet. So I want you to understand how important these two pieces of information are. And these are the pieces of information you're trying to figure out. You're trying to figure out, when do you reach your maximum height? How much time does it take? What is that maximum height? And then also for the minimum height, how long does it take to reach it, and what is it? Now, how many seconds have passed when point P reaches its maximum height for the second time? So that means it takes me 2 seconds to get here. And also remember, frequency. This is frequency. If you want to know the period of the graph, you do the reciprocal of frequency, if you want to think in that way. If I reciprocate this, that is telling me that my period is equal to 10 seconds. That means it's going to take me 10 seconds to do a full round. So if it takes me 2 seconds to get to that highest point at the beginning, I need to add 10 seconds to that to see when I'm at that highest point again. So that's going to be 12 seconds. Now, plot that information where these y values are representing the vertical position of that point P. It is height above the water. The x-axis is representing time, and we are doing time based on seconds. So let's plot these known points. We have, after 2 seconds, 13 feet. I'm going to plot 2 seconds, 13 feet as a point. Then I have 7 seconds, -1 feet. So I'm going to plot the point 7 seconds, -1 feet, right there. Then I also have 12 seconds, puts me back at my highest point again, and that highest point is 13 feet. So I'm going to plot the point 12, 13. Now what I want you to do is try to draw a cycle based on you have a high point, a low point, and a high point. And one thing that could help with plotting, with getting this graph drawn more accurately, is to figure out what those midline points are. My highest and lowest are 13 and -1. What number is halfway between them? What number is halfway between them? 6. Look back at the word problem and think about the number 6 being the midline. What do you notice is so special about 6? What is so special about this location of 6 feet above the surface of the water? That's the location of the center of my circle. This point may start over here, but as it goes around, it's going to go high point, middle point, low point, middle point, high point, and keep going. It reaches its middle point when it's level with the center of that circle. So if this is the midline, I'm going to just do a quick dash graph of it. And what times should I be located at that midline? I'm at my highest point at time 2. I'm at my lowest point at time 7. What time is halfway between 2 and 7? It may not be the nicest number, but what is halfway between 2 and 7? I can add them and I can take the average of their numbers. So 2 plus 7 divided by 2. And do you see that that's 4.5? That gives me some more points. I can plot the midline points to help me with drawing a more accurate graph. Then it's going to hit the midline halfway between when it's at its lowest point and when it's at its highest point. So what's halfway from 7 to 12? In fact, do you see that it's 2.5 seconds to go from a high point to the midline, and then to go from the midline to the low point, and so on. Because remember, we figured out it took 5 seconds to go from the top to the bottom. That means it's going to take half of 5 seconds to go from the top to the midline. The symmetry of these graphs is really, really helpful. And so let's draw that. And then I can plot more points based on just continuing this pattern. And then it should look like that.
Ms. Blanchard?
Yes.
It's 10:43.
Oh, shoot. Thank you. Time's up.